Hi, we're going to look at some notes for 8-9 and 8-10 today. Volume using the disk method, revolving around the x or the y axis. So let's just talk about what we are about to do visually. And I'm going to try and draw it out, and then I think I will show you a video. But imagine I have this two-dimensional shape. It's just a rectangle, and I'm going to say this is some width, and this is some, and actually, we can make this change in x. Delta x we'll say, but it is still the width, and this is r of x. Now I'm using r for a reason that you'll see in a moment. If I take this two-dimensional figure and I rotate it around our x-axis, what happens? Well, imagine taking this thing and moving it around. What's going to happen? I'm going to try and draw it for you. This thing is going to become, I guess I could have just drawn that, a three-dimensional figure where, erase this, where the radius is that r of x, this is still delta x, or a change in x, but imagine I have, of course I have it at school, those really cool paper mache, no, hold on, let me look it up. All right, these are the things I was trying to describe. But if you think about these, and maybe you know what these are and maybe you don't, they start and they're two-dimensional, and then as you open them, they become this three-dimensional shape. So that's what we're looking at. Think about this logically. If we find the area of this circle and then add up a lot of these areas, we're going to be finding volume again. Let me show you one other quick video. So here's just the curve, y equals the square root of x. If we rotate it along that x-axis, we follow this pattern and we see this three-dimensional figure. It is going to be something we are finding the volume of. That is what we are doing in this section. So let's talk about then the volume of a cylinder. So here's a cylinder. I didn't do a very good job of drawing that. Oh my goodness. But the volume of a cylinder is pi r squared times the height, right? Because we're finding the area of this circle, pi r squared, and then we are doing as many copies as this height of the cylinder. That is the idea behind our volumes of revolution. Let's look at what it means for a horizontal axis of revolution and a vertical axis of revolution. So we'll start with our x-axis. So let's say we have this function. Here are our bounds, a to b. And if I take any rectangle here and I rotate it around my x-axis, remember we're finding volume. So we are adding up all of these areas. But when I rotate it, this now is the radius of the circle that gets rotated all the way around here. And we're rotating many, many, many circles to get this three-dimensional shape. So to find this volume, I'm going to take the integral from a to b. We are adding up all of these areas, and the area of this circle would be pi times our radius, pi times our radius squared, and of course this is with respect to x. So thinking about this volume of a cylinder, we've got the pi r squared, and our dx with our bounds is looking at the height. It's giving every single x value along this axis. Sometimes, and we'll do this in a moment, we'll take this pi and we'll pull it out front because of course pi is just a constant, a coefficient, and so we don't need it necessarily in the integral. What if we have a vertical axis of rotation? So what if our function, we can even do the same function. Oh gosh, let me draw that a little nicer. Same function, but in this case, instead of going from a to b on our x-axis, let's say we go from c to d on our y-axis. In this case, we are looking at this horizontal radius, and this radius is now a function of y. This length here depends on which y value on our y-axis we are at. If we are rotating this around the y-axis, again, you can kind of visualize it as a circle where there is our radius. This distance is change in y, and this integral would be from c to d pi times our radius squared with respect to y. Let's look at an example. Find the volume of the solid formed by revolving the region bounded by the graphs of f of x is equal to the square root of sine x and the x-axis about the x-axis from 0 to pi. Use the graph of f, shade the region being rotated, and draw a representative rectangle. All right, so we've got f of x, the square root of sine of x. And notice that they give us labels for the x-axis, so I see 0, pi. I know that this is the region I am rotating. We are rotating it around the x-axis. And so if it helps, and I don't know if this is going to be a very good, when we rotate this around the x-axis, it's going to be like this three-dimensional, what would you say that looks like? I was going to say acorn, but that's not really the right shape. But when it rotates, we get this three-dimensional object, right? Where this is the radius of our circle. And how are we going to actually integrate this? Well, we've got pi times the integral from 0 to pi of our radius squared. In this case, the radius is the square root of sine of x, right? It's this y distance. So the square root of sine of x squared, because we're looking at pi r squared, and this is with respect to x dx. The setup is the most important piece. From here, hopefully, it's not the most challenging integral to calculate. I would start by squaring the square root. So I really have pi times the integral from 0 to pi of sine of x with respect to x. The antiderivative of sine is negative cosine, and we are evaluating that from 0 to pi. I'm going to move this little guy over. Which means I am taking pi, I'm holding that off to the side, negative cosine of pi minus a negative cosine of 0. Cosine of pi is 1 minus a negative cosine of 0 is also 1. All right, I paused it because I think I said something wrong, and so I want to just go back. I'm sorry. I'm actually going to draw a quick graph of cosine so I can help myself visually. Cosine looks like this. This is 2 pi. That means this is pi. All right, let's try this again. So cosine of pi is negative 1, but we've got this negative minus negative cosine of 0 is 1. Oh my goodness, that's a lot of negatives. That's why I was getting a little bit tripped up. So we have a positive and a positive. I'm getting 2 pi. There we go. I apologize for that. But really, it's the setup that's the most important. Think about it again as we are rotating a circle with a radius of whatever that y value is. And the area of the circle is pi times that radius squared, and then because we are integrating it, we are adding up all these copies for our bounds. We're going to look at 810 as well because it's the exact same idea, but it's just revolving around something that isn't the x-axis. It says find the volume of the solid formed by revolving the region bounded by the graphs of 2 minus x squared and y equals 1, about the line, y equals 1. Sketch the graph and draw a representative rectangle. All right, so first we're going to start by graphing the line, or the curve, I guess, 2 minus x squared. I could also write this as negative x squared plus 2. So I know we go up to 2. And then depending on kind of how you want to look at this, I might plug in a value of 1, f of 1, negative 1 squared plus 2. And so I'm getting 1. That means I've also got negative 1. And honestly, that's, oh my gosh, that was so bad. I'm so sorry. Okay, well, that's not the best parabola, but whatever. That's about as much as we need because, maybe I'll do this. Because look at our other function. Our other function, so this is f of x, g of x is the line y equals 1. This is our region we're interested in. And it says we are rotating this about the line y equals 1. So we're actually rotating it around this little guy right here, not around the x-axis. To figure this out then, we need to ask ourselves, what is this radius? And we're going to actually use the things we've already learned before, that this radius here is whatever this blue distance would be, minus this green thing. So my radius, r of x, is equal to my f of x function minus my g of x function. In this case, my f of x function is 2 minus x squared minus my g of x, which is 1, which would give me 1 minus x squared as the radius of this region. Now that we have the region, or excuse me, now that we have the radius, finding the region, sorry, I had to pause because I had to cough. Finding the area of the region hopefully will not be so challenging. I know my bounds because they are laid out for me in my drawing. So from -1 to 1, I want to get that pi. I'm going to pull it out front because I really don't need it. Pi times the radius squared. Well, we know our radius is 1 minus x squared squared, and we are doing this with respect to x. And I am going to actually change this, and I think I talked about this in another video, but I'll say it again, because what I notice is this graph is perfectly symmetric. And sometimes it's easier to evaluate integrals when they start at 0. So instead of doing this entire integral, I'm going to say, because I know, I'll draw this over here. Oh gosh. Because I know this half is going to be the same as this half, I can write this as 2 times the integral from 0 to 1 of 1 minus x squared squared dx, and I don't want to forget that pi. And now we can evaluate this by, well, we're going to have to FOIL this little guy first. So I'm going to say 2 pi times the integral from 0 to 1 of 1 minus 2x squared plus x to the 4th dx, 2 pi times, and now I'm going to take the antiderivative of this little guy. So we have x minus 2/3 x cubed plus 1/5 x to the 5th. And we are evaluating that from 0 to 1. Like I said, I like doing this because evaluating it at 0, well, notice all of these pieces would have 0, and we don't need to worry about that. So I really just need to plug in my 1. So now I have 2 pi times 1 minus 2/3 plus 1/5. Of course, you can type this all into your calculator, or we can take some time to remind ourselves about adding fractions. Either way you want to do it, hopefully you get 16 pi over 15. The real thing, though, that we want to really focus on is the setup. So hopefully the setup was good and made sense for you. Check back in a little bit for a video on 8:11 through 8:12.